Hello and welcome to our course on calculus. My name is Bruce Edwards, and I'm a professor of mathematics at the University of Florida. This course is going to cover the content of the Advanced Placement AB examination. And that is just about the same as first semester college calculus. So who am I? Who is Bruce Edwards? Let me tell you a little bit about myself. I went to Stanford as an undergraduate and graduated in 1968 in mathematics. And then I joined the Peace Corps. And for 4 years, I taught mathematics in Colombia, South America. I actually taught in Spanish. Then I returned to the United States in 1972 and went to Dartmouth, where I earned a PhD in mathematics in 1976. And I've been at the University of Florida ever since. Let me add that I'm a textbook author. My co-author is Ron Larson. He's at the Penn State University. And in fact, the content of this course is based on our calculus textbook. Together, we've written books in calculus, pre-calculus, trigonometry, algebra, business calculus, and even linear algebra. That said, though, any calculus book would work as sort of a backup source of information for these videos. Our textbook actually has been used widely, not only in universities, but in high schools, in advanced placement programs. I've actually been a grader of advanced placement examinations 4 times, so I'm quite tuned in to the world of advanced placement calculus. And finally, let me add that I teach calculus. I teach calculus all the time at the University of Florida, and I really enjoy it. I enjoy freshman calculus for a number of reasons. One is the subject is so pretty. Calculus really has some neat ideas, and we'll see some of these cool connections and applications in this course. And also, I enjoy the enthusiasm of the students. They tend to get excited about calculus because they see how useful it is in their careers, in their majors. Now, one of the goals of this first lecture is to try to answer the question, what is calculus? That's difficult to answer. And in fact, you might say these 36 videos will answer that question because you'll see calculus in action. But let me try to give you a taste of what calculus is about with a couple of examples. Many people say calculus is the mathematics of change. Let me give you an example of that. Suppose you're driving from Atlanta to Miami, and let's assume the trip is 600 miles, and suppose it takes you 10 hours. What's your average velocity? What was your average speed for that 10-hour trip? Well, you did 600 miles in 10 hours. Basically, 60 miles an hour would be your average speed for that trip. But is that what your speedometer shows? As you're driving down the road, your speedometer changes. You're going 70 miles an hour, 30 miles an hour, etc. The speedometer shows the instantaneous change in velocity. Let me say it as the instantaneous velocity. Whereas the average velocity is over a long time period. Somehow the speedometer is able to tell you the velocity at a particular time. That's sort of the essence of the calculus. Another aspect that defines calculus is that it's a field with lots and lots of really important applications. And we'll see many of those in this course. We'll be able to find areas and volumes of complicated regions and solids. We'll study particle motion. We'll study applications like carbon dating in the field of geology. And we'll look at things like compound interest in the field of business. So I think you can see now why we need to study calculus. It's basically the foundation for science, for physics, chemistry, biology, engineering, economics, etc. At universities, calculus is the prerequisite for many, many, many majors. My classes, when I teach calculus, are full of pre-med students, engineers, physics majors, environmental engineers, finance majors, etc. But finally, let me give you what I think is the most important reason to study calculus, and that is it's really beautiful. It has some great connections, some surprises, and some results that just will say, whoa, I don't believe that, and yet calculus says they'll be true. Let me show you something about the beauty of calculus. You might have been to St. Louis and seen that lovely arch next to the Mississippi River, the so-called St. Louis Arch. Well, the shape of that arch is a catenary, and we'll see a catenary in this course. It's a very special curve. It's not a parabola. And it's an engineering marvel that they were able to construct that St. Louis Arch, and they used the catenary as the basis of that construction. Good. I'd now like to take a closer look at a particular problem in calculus that will illustrate one of the core ideas. This is called the tangent line problem. And I think you'll enjoy seeing some of the calculus ideas come to life here in this first lecture. It's what I call a classic problem, meaning it's hundreds of years old. And yet this problem, although it'll seem fairly straightforward today, turns out to be the foundation of what we call the derivative. You might have heard that word derivative. It's a word that means rate of change. And we'll study the derivative after a few lectures on pre-calculus and limits. It's the differential calculus that we are illustrating now with this tangent line problem. Later on, we'll focus at the so-called integral calculus. So let's turn to this tangent line problem. I should say it's relatively new. It was worked on in the 1600s, and then along came Isaac Newton and Gottfried Leibniz. Isaac Newton in England and Leibniz, of course, in Germany. And independently, they kind of put the tangent line problem and the rest of calculus together into a package. They're often thought of as being the two mathematicians that invented calculus. That's not quite right. I think really they kind of put together the ideas that were being talked about for hundreds of years before their time, but they packaged it up into a finite field, a finite discipline. It's interesting to note that they did all their work independently of each other, and their notations, for example, are completely different, and they disagreed as to who was the inventor of calculus. There were lots of fights back in those days as to who did it first. So let's focus on this tangent line problem, this core idea of the differential calculus. First of all, what do we mean by a tangent line? Well, I think you know what a tangent line to a circle looks like. It's a line perpendicular to the radius that touches the circle at one point, as I've indicated in this figure. That said, what's the tangent line to a more complicated curve? Say a parabola. How would you find the tangent line to a parabola? Here's a picture of an arbitrary curve, and I've drawn a tangent line to that curve. How could you find the equation of that tangent line? Well, you'd have to find its slope, and you know a point, the point P. So that's going to be our goal in the next few minutes. We're going to talk about finding tangent lines to more complicated curves. But I'd like to be very specific here to make things a little bit easier to understand. Let's select a very simple curve, say the parabola y equals x squared. You know what a parabola looks like. And we'll pick the point 2, 4 on that parabola. Let me say that this is my favorite problem. I do this problem every time I teach calculus, and I usually do it one of the first or second days of class. I find the tangent line to this parabola at that point P. So how are we going to find this tangent line? We're going to calculate its slope, and then we'll use the point slope formula to find the equation of that tangent line. Good. Here's a picture of our situation. There's the parabola y equals x squared, and I've indicated the point 2, 4, and I've drawn what I think the tangent line looks like there, and that's what we're trying to find. So how could we do it? Well, here's how the mathematicians back in the 1600s solved this problem. They took 2 points, one being P and another point Q nearby, and then they computed the slope of those 2 points and then had the point Q get closer and closer to P. Well, I used the word slope there, didn't I? And let's take a moment to review slope. Slope is what I call a pre-calculus topic. The equations of lines and slope are pre-calculus topics, algebra topics. One of my goals in this lecture series is not only to cover calculus, but to also take time to remind ourselves of the pre-calculus skills we need to be successful in calculus. For example, we're going to have to know how to find equations of lines. That's one of the basic skills of pre-calculus that will play a major role in calculus. So let's remind ourselves right now, what is the slope of a straight line joining 2 points? Let me show you a picture. Here's 2 general points. The coordinates are x1, y1 and x2, y2. And I draw the line joining those 2 points. And what do we mean by the slope of that line? Well, geometrically, you mean it's the change in the y values, the vertical change, divided by the change in the x values, the horizontal change. Mathematically, you do the following. Slope is defined to be the rise over the run. So it's the change in the y values divided by the change in the x values. We'll generally use the letter m to indicate slope. And the difference in the y values divided by difference in the x values is y2 minus y1 divided by x2 minus x1. That's the definition of slope. Let's do a quick example to make sure we're comfortable with that definition. Let's take the point P, 2, 4. That's the point that we're using in this example. And let's take a nearby point Q with coordinates 3, 9. You might notice that Q is also on my parabola, isn't it? Because 3 squared is 9. So both of these points are sitting on the parabola. Let's find the slope joining P and Q. Well, the definition says difference in the y values divided by difference in the x values. So I subtract the y coordinates, 9 minus 4, divided by the difference of the x coordinates, 3 minus 2. And then I simplify that to be 5 over 1, or 5. Notice, by the way, a slightly tricky point here. I subtracted 9 minus 4, and I made sure I did the other subtraction in the same order, meaning don't write 9 minus 4 divided by 2 minus 3, but rather it's 3 minus 2. It's the q coordinates minus the p coordinates. Good. And this line, by the way, has a slope of 5. That means it's fairly steep. It's rising 5 units vertically for every 1 unit horizontally. Good. Back to our tangent line problem. How are we going to find the equation of this tangent line? Well, the idea is very clever. This is really, I think, you'll find just very neat mathematics here. Here's what they did. They took a neighboring point, I'll call it Q, and its coordinates will be x squared because Q will also be on the parabola. So P has coordinates 2, 4, and Q has coordinates x squared. Good. And we can calculate the slope joining P and Q. They often call that line a secant line that joins P and Q. Well, what's the slope of the line joining P and Q? Well, it would be the difference in the y values divided by the difference in the x values. So it would be x squared minus 4 divided by x minus 2. So if you pick any x value you want, except for 2, you can't divide by 0 in mathematics. But for any other x value, you could calculate the slope of PQ, couldn't you? For instance, suppose x is 3. Then my slope would be 9 minus 4, 3 squared minus 4, divided by 3 minus 2, or 5. In fact, that was the previous example I did. So for every x value different from 2, we can compute the slope of PQ. Good. Now, with this idea in mind, how are we going to find the slope of the tangent line? Well, I think you can see in the picture that the slope of PQ is close to the slope of the tangent line. It's not the slope of the tangent line. The slope of PQ is 5, and the slope of the tangent line is not quite as steep as 5. But how could we get a better approximation? What could we do in order to find the slope of that tangent line? Well, let Q motor down the parabola, get closer and closer to P. Algebraically, let x get closer and closer to 2. And as it does, that line PQ gets closer and closer to the tangent line. So let's do a numerical study now. Here's what I'm going to do. I'm going to take various x values and then compute the slope of the line PQ for that x value. For instance, when x is 3, we just did that, the slope turned out to be 5, didn't it, in that equation for slope? Well, if I take x to be 2.5, now I'm closer to P, aren't I? I'm getting closer and closer. The slope turns out to be 4.5 in that formula. Let me get even closer. How about if x is 2.1? Well, the slope now is 4.1. How about if x is 2.0001? I am really close to P now, aren't I? P and Q are almost touching each other. And the slope formula turns out to be 4.0001. Well, then you might say, what about on the other side? What if Q were below P? How about letting x be 1.9999? That means Q is really close to P, but slightly below P. Well, the slope turns out to be 3.9999. In each of these calculations, I'm using that slope equation that I developed, x squared minus 4 divided by x minus 2. Well, let's make some guesses as to what's going on here. Can you see a pattern? Can you see what's happening here? What do you think the slope of the tangent line is, given this graph here, this data? Well, I hope you say to yourselves, hey, it looks like the slope is 4. Great. So let me summarize what we did. As x gets closer and closer to 2, the slope of our secant line PQ got closer and closer to 4. Let me say it a little bit differently now, in a little more subtle manner. I can make the slope of that secant line as close to 4 as I want by suitably selecting an x value sufficiently close to 2. It's kind of backwards there. Good. Now let's look at this algebraically for a moment. Remember, the slope was change in y over change in x, and in our case it was x squared minus 4 over x minus 2. Now we can do a trick here. If x is not equal to 2, in other words, if p and q are distinct, the slope formula can be factored. The numerator can be factored into x minus 2 times x plus 2 divided by x minus 2, and then you can cancel the common factor, and you're left with a very clean and simple formula for slope. The slope is x plus 2. Okay. Before I go on, notice something that just happened here. We did some pre-calculus, didn't we? We did some factoring. And that's a skill that we will use over and over again in this course. Factoring is, in this example, fairly easy. In real life, factoring can be very, very difficult, it turns out. But the problems that we'll look in this calculus course, I'll try to construct them so the factoring won't be a burden on us. But again, this is a pre-calculus skill that I hope we're somewhat comfortable with. Again, the two lectures that follow this lecture review pre-calculus, and we'll see factoring again. So let me recap our situation with the tangent line problem. Geometrically, Q approached P, and as it did that, the secant line PQ approached the tangent line at P. And algebraically, while we were doing that, as x gets closer and closer to 2, the slope of that secant line, which was x plus 2, approaches the slope of the tangent line. And calculus will tell us that the slope of the tangent line at 2 is precisely 4. 2 plus 2 equals 4. That will be the calculus step. We are doing what you say, taking a limit, and the limit as x approaches 2 of x plus 2 is 4. Let me make some comments about what we just did. You might remember earlier in this lecture I talked about average velocity and then the instantaneous velocity of your automobile that the speedometer indicates. I hope you sort of see a parallel with what we just did with the tangent line problem. Think of the slope joining P and Q as an average velocity. And then we took a limit down to where we had an instantaneous slope at the point P equals 2, 4. So there's kind of a parallel here, that the average velocity corresponds to those slopes of the secant lines, and the instantaneous velocity corresponds to the slope at the point P, the slope of the tangent line. Let me show you something else you might get a kick out of, some notation that we'll use when we study limits in lectures 4, 5, and 6. Here's the notation of what we just did. We were asking the question, what happens to the slope, which is x squared minus 4 over x minus 2, as x approaches 2? In other words, using the limit language, what's the limit as x approaches 2 of the quotient x squared minus 4 over x minus 2? Well, we simplified that, remember, by factoring the numerator. So that's equivalent to the limit problem, the limit as x approaches 2 of the quantity x plus 2. And the theory of limits says in this latter case, we'll be permitted to just plug in 2 and get the final answer of 4. Great. We now know the slope of our tangent line at the point P. Well, let's find the equation of the line now. If you know the slope and you know one point, there's a formula called the point slope formula that gives you the equation of the line. And we'll review that formula next time, but I think you probably remember it. Here's how it goes. Y minus 4 equals slope 4 times x minus 2. And then you simplify this equation. Y minus 4 equals 4x minus 8. And then move the 4 to the other side, and you get the tangent line, y equals 4x minus 4. So this is really neat, I think. We have our parabola, and now we have our tangent line. So we can graph these together in the same viewing rectangle, in the same coordinate system. Here's a picture of our parabola again, and the point 2, 4. And now I've drawn that line, y equals 4x minus 4. And notice that it touches the parabola at P. It kisses it once and then goes on. And in fact, I invite you to do the following, and this will be something that I'll encourage you to do throughout the course. Take your graphing utility, your graphing calculator, and graph the parabola and graph that tangent line together to try to reproduce this picture. And then do something that's kind of fun. Zoom in near the point P. And what you'll observe is that the tangent line and the parabola look like they get really close together, because the tangent line locally near P is a very good approximation of the parabola. Great. Okay, let me draw some conclusions about this problem. This tangent line problem, as I've said earlier, is a typical example of what we call the differential calculus. It involves the idea of limits, and we will discuss limits after a pair of review exercises, review lectures that I'll be doing, lecture 2 and 3 coming up. Now, students often ask me, Professor Edwards, what makes calculus difficult? Why aren't I doing very well in your class? And after many, many years of teaching calculus and teaching mathematics, I sort of have a good idea of why calculus, I think, is difficult for some students. On the one hand, it requires pre-calculus. I pointed out even in that last example we did, some instances where we needed some pre-calculus. We needed to factor something, we needed to find the equation of a line, and as we go through this course, we'll have to talk about trigonometric functions, inverse functions, etc., graphing functions. So we'll be using lots of pre-calculus. Again, I'll make an effort to indicate the places where pre-calculus is coming into play and remind you of those skills. Also, calculus takes practice. All of mathematics takes practice, but calculus in particular. You have to solve problems yourself. It's one thing to watch me in the video do an exercise and show how to solve a problem, but it's better if you try to do it yourself. I like to talk about, tell my students, it's like becoming a basketball player. If you want to be a good basketball player, it won't be enough just to watch others play basketball, will it? You have to shoot the baskets yourself. That's how you become a good basketball player. And the same is true of calculus. You have to do the problems yourself. Fortunately, we have a workbook that goes along with this course, and in there we have exercises, and I invite you to attempt to do those exercises after you've gone through the corresponding lecture. So what will our course cover? What will we be doing in our course? As I said at the very beginning, this course covers the topics of the A-B examination of the Advanced Placement Program. That is precisely, or almost precisely, the content of a first semester university calculus course. The topics we'll cover in particular are, well, first those pre-calculus reminders, and then we'll cover limits, what we call derivatives. We'll do applications of derivatives, and then we'll turn to the integral calculus and study integrals, and then the many applications of integrals. This is very, very similar to the calculus course I teach at the University of Florida. Again, we have a workbook that goes along with the course. I invite you to look at the workbook ahead of time. Say before you look at the lecture, get an idea of what I'm going to do, and then maybe after the lecture you can look back at the workbook. You'll see some of the same examples in the workbook that I'm doing in lecture. And then you could try the exercises. See if you can do the problems in the workbook. All the worked out solutions are available in the workbook. Some of the good features about these video courses is that you can stop the video anytime you want. When I teach calculus at the University of Florida, they can't stop me. I just go on. I just keep lecturing. And if a student misses an idea, tough luck. But the good news here is you can stop the video anytime you want, and you go back and look at it again. I invite you, like university students do, take notes as you're doing mathematics. A lot of learning goes through the arm and up to the brain. And of course, please have a graphing calculator around to verify some of the answers. We'll be drawing lots of pictures in this class, and it's nice to have a graphing calculator to confirm your algebraic work. So how could you use this course? Well, I think it's pretty obvious that this video could supplement your own calculus course. You might be preparing for the advanced placement examination or other tests, and you could look at the video lectures to remind yourselves of key calculus ideas. Or you might be thinking of taking calculus in the future, and you could get a good idea of calculus by watching these videos. Or perhaps on the other side, you took calculus a long time ago, and don't remember very much, well, look at the video and you can say, oh yeah, I remember derivatives. Oh yeah, I remember that. It'll all come flowing back. And of course, you can see how calculus can be used in the workplace. You might be an engineer or an architect and need to use calculus on a day-to-day basis. And finally, I think, teachers might find it curious to look at my videos to see how I explain an idea, and they can either copy that or say, I don't like that explanation, and do something else. But it's always interesting for professors to watch other professors teach ideas. Great. So what now? What are we going to do now? Well, as I said, the next 2 lectures, I'd like to focus on key pre-calculus ideas. We're going to look at some graphing, lines, then we'll talk about functions, often said to be the most important topic in all of mathematics. And in particular, we'll spend some time on the trigonometric functions, the sine function, the tangent function, etc. As I said, I'll be pointing out throughout the course where we'll need these pre-calculus ideas. So thank you very much for sitting through Lecture 1 with me, and I look forward to seeing you next time.